It's arcade time. Let's go. So we're playing some pinball. The ball has a mass of 50 grams. So immediately I will convert that to SI units. So 50 grams, 0.05 kilograms, 10, 100,000. Yep. And the spring constant, okay, of the launcher is 100 newtons per meter. So that's already in SI units, newtons and meters. And that tells us how stiff or how soft the spring is, right? How much force it can apply to the ball as you pull it back. Now, question A, you pull back the spring launcher 5 centimeters. So again, let's just convert that to meters straight away, which I think is also 0.05 divided by 10 divided by 100. Yep. So you pull back the spring launcher. I'm just thinking, do you guys all know what pinball machines are? Surely. So it's an arcade machine where at the bottom there's a little knob that you pull out, and it's attached to like a spring with a ball on it, and if the further you pull it back and then let go, the more force is applied to the ball, and it shoots up and it bounces back around, and then you have these little levers at the bottom that you can whack it up and down. If you don't know what it is, look it up, play it, it's great. Now the first question is, how much force is imparted onto the ball? Right? So you've pulled it back 0.05 meters, you let go, how much force is applied to the ball? So let's take note of what we have. We have the spring constant, we also have a mass, and we have a distance. And we are looking for a force. So looking at our formula sheet, we know that Hooke's law, F equals negative kx, where the negative just tells us like the direction of the force, whether that's on the spring or on the object. So in our case, we can actually ignore that because we're just talking about the magnitudes. Now, the spring constant is given as 100 newtons per meter, and x is the distance you pull the spring back from equilibrium. So in this case, we pulled it back 5 centimeters, so that will be our x value, how far it's stretched away from its usual position, its equilibrium position. And actually, we don't even need a calculator for that. All right, what is that? That's 5 newtons. So after pulling the spring launcher back 5 centimeters, letting go, the ball experiences 5 newtons of force in that moment from the spring. Right, and that's using Hooke's law. Question B. Now, pinball machines aren't flat. They're usually on an angle. In this case, it's on a 45-degree angle. Calculate the component of the weight force in the direction of this incline, this angle. And that's given us a hint to draw a free body diagram first. So let's do that. So I will draw the incline. So here's our pinball machine on an angle. And here is our ball. With me so far. Now, the weight force of an object acts towards the center of the earth, and usually on paper we draw that as an arrow, a vector, going vertically downwards. So that is our weight force. Now, it's asking us to calculate like the value, the component of it. So let's first calculate the weight force as is, because we know its mass, 0.05 kgs. So we'll go weight force of ball is the mass of the ball times gravity. Mass of the ball 0.05 kgs times 9.8 0.05 times 9.8, 0.49 newtons, right? It's a weight force. So that's the weight force, and it's asking us to find the part of the weight force that is acting, in this case, down the hill, right? Down the ramp. So with all two-dimensional like kinematics or forces problem, we should define a coordinate system, and in this case I will put my axes like so. So where I have my x-axis in line with the ramp, and then my y-axis perpendicular to that. Right, so in kinematics problems, thinking back to like projectiles and things, we usually want horizontal and vertical, right? Because gravity is acting down, that makes sense. But for a problem that's on a ramp, not always, but sometimes, we like to put it in line with the ramp to make the calculations a bit easier. So, looking at our weight vector, we could split it up into a y component and an x component. And the question asked us to find this x component, right? The weight force, the part of the weight force that is in line with the ramp. And we know the angle in here is 45 degrees. And that will actually correspond to this angle right here as well. And so let me just redraw that triangle a bit bigger. So we have our weight force, 0.49 newtons. We have that component, which we don't really care about. And we have the component we are looking for, 45 degrees. So from that, thinking of our trig ratios, we are looking for opposite the angle. We are given the hypotenuse, so we will use the sine ratio. So sine of the angle is equal to the opposite over hypotenuse. In other words, the x value, or the component of the weight force in the x direction, is 0.49 sine 45. So let's compute that. Make sure your calculator is in degrees. 0.49 times sine of 45 degrees. 0.35 newtons. So this is saying that part of the weight force, in fact 0.35 newtons, is acting down the slope. Not vertically downwards, right? That is the entire weight force, but part of that is acting down the slope. Cool, so that's part B. Now, using our answers to A and B, calculate the acceleration of the ball as it is launched. So a reminder, part A told us that 5 newtons goes into pushing the ball, and part B, we found that the ball is going to resist that with 0.35 newtons, right, in the direction of the slope. So let's put it together. So again, with our ball, we know that 5 newtons goes into pushing it upwards, up the ramp, and what was that, 0.35 newtons goes to resisting it. I will ignore frictional forces, but that would be a little bit as well. And we also know that some of the weight force goes this way, and we can assume that the pinball machine would provide a support force, right, that's equal and opposite, which is why we can actually, for this instance, ignore those forces, because we're looking at its acceleration up the ramp. But yeah, just keeping in mind they are still there. So again, our coordinate system, x and y, we've just mentioned that in the y direction, the net force will be 0, they're balanced. In the x direction, the net force would be 5 newtons, right? Positive 5, because it's going with my coordinate system, right? So positive is up the ramp. Take away 0.35, because it's going down the ramp in the opposite direction, leaving us with 4.65 newtons of a net force. And why do we need the net force? Well, the question did ask us to find the acceleration, and we know from Newton's second law that the net force is mass times acceleration. So solving for acceleration, net force divided by mass, which the net force is 4.65 divided by the mass of 0.05 kgs. Let's double check. Yep. And so computing that, 4.65 divided by 0.05 gives 93 meters per second squared. Now that may seem like a ridiculously fast acceleration. It is. But keep in mind that is only for a split second as you let go of the spring. Immediately after that, frictional forces will come into play, and the weight force is the only thing acting on it, so it would decelerate quite rapidly. But I'll be honest, I did make up these numbers, so there's that. Cool, so that's part C. Just to recap that, in part A, we found the force applied onto the ball by the spring. In part B, we then worked out the part of the weight force that goes down the ramp. Right, we use vector components, so we drew our right angle triangle, we used our sine ratio to find the component, so that in part C, in the x direction, we could work out the net force as 5 minus 0.35, right? The force from the spring minus the part of the weight force down the ramp, so that we could work out the acceleration. Now, part D, describe the motion of the ball immediately after it is launched. Refer to the forces acting on the ball and their relative sizes. So, again, let's draw the diagram, because it is so very helpful. After it is launched, it tells us that the spring is no longer pushing it. Right? The spring's done. It's done its job. Now the ball is just moving with its own momentum. But what are the forces acting on the ball? Well, of course it has a weight force. Let's do our coordinate system again, x and y. It has a weight force which can be split up into a little bit down the ramp and a little bit into the ramp. So that's the weight force. It would have a equal and opposite support force, right? Otherwise it would be falling into the pinball machine, like damaging it, or it will be flying away, which is unreasonable. What other forces are there? Is there anything pushing it up the ramp? No, not anymore. There's no spring or mini thrusters or anything. So the only other force acting on it would actually be friction, right? A combination of the friction, like the contact friction, and air resistance. So looking at this diagram, the net force, if net is 0 in the y direction, right? Because the support and the component of weight cancel, they're equal and opposite. However, the net force is not 0 in the x direction. In fact, it will be acting down the ramp, which means accelerating down the ramp. Or you could say it's decelerating, right? Immediately after it's launched, it starts to decelerate due to the weight force, due to weight and friction. Cool. Now, if you've actually played pinball, you'll know that it's sort of curved. So after you launch it, the machine's sort of curved at the top. So it'll follow that path and then fall back down the pinball machine. Alright, so that does it for this question. I guess homework is to go to an arcade and play some pinball and think about all the physics involved. See ya.